I suppose everybody is interested in cosmology, whether they know it or not. Because at night, everybody wants to look up in the stars, and they've been doing that from the year dot and wonder. Because when you look into the heavens, the question arises, where did all this come from? And where did I myself come from as well? And that's a very poignant question. There are many people who have many different understandings of it. But it begins with this sense of awe about this vastness of space and what it contains and why it's there, and where do I fit into this whole thing? So people have asked themselves if ours is the only planet that supports life, and there are planets, stars, galaxies that we know now, but it was only very recently that we knew this. Only, let's say, from the 1960s onwards, did it occur to us that actually there are more than this Milky Way that we have. I think it was 1960s, probably maybe earlier than that, but not long in terms of our understanding of what is there. And of course, in the Western Hemisphere, it was always understood that everything revolved around the Earth. It was a geocentric position, and we hold on to that geocentric position for practical purposes. So I often say to people, if you look at the stars and you say, I look up into the sky, I try to correct them and say, why are you saying up? Why don't you say down? If you lie on your back and look into the sky, you'll get, and use this term down, you get a much better, more accurate perspective, because outside of the Earth's atmosphere, what is up, what is down, what is left, right is right, we just don't know any of these things. So it's a wonderful world if we explore it. It's centered around astronomy. Astronomy is a science that seeks to explain everything that we observe in the universe. And we can try to look for echoes of what are the current cosmological models, collectively called Big Bang theories. And we can do this by studying the cosmos beyond our own planet. So it's interesting to see what some of these approaches were or have been and are now. I suppose it was the 1930s that presented us with revolutionary advances and concepts in cosmology. In the early 1940s, the Second World War limited any exploration in science in general. And any of the scientific discoveries that were made during that period, like many, many aspects of so-called modern life and civilization, it was all really based on how can we advance our technology in order to win at a war. And so there were various advances, of course, in terms of this war, in terms of nuclear physics. And these also helped us to transform our cosmological speculations into quantitative calculations. A line of investigation began in the 1940s, and it was pursued mainly by physicists, not astronomers. And there's always this dichotomy between physics and astronomy. So let's be clear. Astronomy looks and tries to gather the observational facts. But increasingly, modern physics has tried to make speculations. They did this following a model set by Einstein. Einstein's many discoveries were really as a result of his doing thought experiments. Now there's an area called theoretical physics where everybody's doing thought experiments and where there's an urgency to go and get a Nobel Peace Prize. But what if the very foundation of our physics is wrong? What if the very foundation of our cosmology, which is there in every textbook now, studied at every university, is wrong? And why would it be wrong? The only reason why it would be wrong is because we've put in a hypothesis of something, not based necessarily on the observational evidence, but we've taken observations and tried to fit it into and squeeze it into a straitjacket, some cosmological theory. Now, it began, of course, with this observation from Edwin Hubble, who, with his astronomy, with an advanced telescope, managed to see a phenomenon called redshift. Redshift is shifting the wavelengths of light so that they are lengthened. The reason why we see blue sky is because the wavelengths are short. And the inference of wavelengths being long means some object is traveling away from us at a greater speed. And what's happening, of course, is that means that the wavelengths or the waves of light that we receive optically appear to be red. That is shifted to the red end of the visual spectrum. And so he made a correlation between distance and the redshift. What is redshifting? You may not know much about redshifting, but you do know about ambulances or fire engines. You do know that they come and there's a high pitch and then it goes away. Something like ding, 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 like that, and it goes away. If that is true with sound, then it also happens with light because both are based on wavelengths. And they're all part of the electromagnetic spectrum. One is photons gathered together and formed as wavelengths. And the other one is to do with audio waves. The principle is the same. Now, there are many explanations. There are probably 2 or 3 more explanations, actually, as to why there should be redshifting. Why should it be observed? Not necessarily that things are moving away from us. If we want to think outside the box, it could be that we are shrinking, that things are going inward, not outward. That's one explanation. Another explanation is it has nothing to do with any Doppler effects or redshifting as such in terms of distance, but it could be a phenomena to do with quasars. And so there has been work done which has tried to convince people that quasars are not that distant. Quasars, very, very bright, bright objects in the sky. And when they pulse, of course, then the pulsing itself could cause a distortion of light and could cause a redshift. But let's take for granted that things are moving away from us at a rapid speed. The natural conclusion then is, if there's a movie that is running like that, if we reverse the movie, run it backwards, then we'll come to an origin. Add to that fairly recent discoveries about black holes from Roger Penrose and from the late Stephen Hawking, and see that there is an event horizon at the center of every galaxy, more or less. These are called black holes. Some of them are very big, some of them are quite small, but it's a kind like a plug hole or a drain hole down which water swirls and disappears. As it's moving over the precipice, this is called the event horizon. Beyond that, the time and space has no meaning. Beyond that, they say that, initially anyway, that energy cannot escape and information cannot escape, but this violates some laws within physics. And so they discovered that, no, actually, there are black holes that leak. It's called Hawking radiation. And we can pick that up and we can measure it. And a wager was there with Stephen Hawking and a man called Leonard Susskind. Leonard Susskind said, no, information cannot be lost because there's a law of conservation to do with information also. And you are now violating this law if you say all information is lost. So he was able to win his wager against Stephen Hawking. And so something goes in and something comes out, but it's transformed. But what is there in between this, we have no idea. And this no idea is called singularity. Singularity means we cannot postulate in it any beginning, any end. Time does not exist and space does not exist. In fact, the speed of light is so great when it goes in because of its gravitational pull that time itself stands still. And time and space are two sides of the same coin. So if that's standing still and that's non-existent, what is existent? Let us apply the same principle when we wind a movie backwards and say, things are moving outward at a rapid speed and away from us being the observer. When you wind this movie backwards, you're sure to get something like a black hole. It's another way of saying nothing. Now, the problem with that, of course, is how we get something from nothing. How we get, in the language of the Vedas, how we get existence from non-existence. It becomes a very big problem. Supposing that we think we can get over this problem, then we're left with unknown physics. We're left with quantum physics. The only way to explain what happens within a black hole is to resort to the smallest possible components of physics today, and that is in the realm of quantum physics. And in quantum physics doesn't behave as Newtonian physics behaves. A table is not a table in quantum physics. There is no speed there in the sense that we know it. That is, there's no transit from A to B. Things happen instantaneously. Let's take an electron. An electron, nobody has ever seen. They've seen kind of flashes and evidence of such a thing, the effects of it. But it's not a thing and therefore doesn't do what things do. We have a model of an atom that was developed by Niels Bohr. It's something like we're involved in a planetary system around a solar orb. This solar system, and again, we can say a galaxy with a central axis, and everything's rotating around it. So could this be a model that we can use for the atom? Bear in mind, the idea of an atom was way back in ancient Greece, and is also there in ancient Indian philosophical concepts as Anu, the smallest possible unit that we could ever think of, which has to be a basic building block. The word atom means something that you cannot go smaller than it, but from the 1920s onwards we knew, yes, you can go smaller. In fact, the fundamental particles there are, in those days anyway, termed protons. Protons, neutrons, electrons. But protons themselves, we know, have been broken down into quarks. And now we have a standard model within physics that has taken the zoo of all these very, very weird and wonderful particles and systematically put them into an order of a dozen. Electrons are part of this. Now, electrons, if we were to take an atom, and the center of the atom, the nucleus of the atom, protons, neutrons, is something like the size of a small ball that you can throw. The nearest electron is something like 4 or 5 kilometers away. And when you look for it, you won't find it. Because along with this quantum physics is a very special hinging kind of law, and it is Heisenberg's uncertainty principle. And that means that if you want to find the location of a particle, then you won't know how fast it's going. And if you try and find out how fast it's going, you cannot find its location. This is called the Heisenberg uncertainty principle. And this is an uncertainty principle, not a certainty principle. And what that means, therefore, is that when you, the certainty of a location of a particle increases or decreases, the uncertainty of where it is commensurate with the uncertainty, or the certainty, if you will, the other side of the coin, of how fast it's moving, and vice versa. So you can't really measure its energy and at the same time pinpoint it. And for that reason, electrons don't do what things do. If you ask for a definition, what is an electron? It's a vibration or an oscillation, depending on how you view it, in Hilbert space. It doesn't tell you anything. So when we use the term quantum leap, and you use Niels Bohr's model, a kind of planetary model, that is a proton in the center and everything else moving around it like satellites. If you use that model, then you have to insert something called Pauli's exclusion principle, which says electrons are not happy to share their orbit. And when their energy is knocked off, they slide from one level, as it were, to another, but not in time. It's like transferring money from a bank. If you transfer money from your account to my account, you don't have to come here to Dublin and deposit it in my bank account. It disappears in your account and appears in my account. Same thing with electron. It disappears in one place and reappears in another spontaneously. And this spontaneity was an unhappy view from Einstein's point of view. He felt, no, these things cannot behave in this way. And then when you go further and see that a change in one atomic unit, let's say a change in a photon, no matter how distant, but of course, a photon travels at the speed of light. But if you take another unit and you change its magnetic direction, what we call spin, these two particles having previously met and associated, no matter how far distant you put them, then they know what's happening on the other side, and spontaneously and instantaneously they change. And this has been proven through experiments around Bell's, what's called Bell's theorem. So this was unacceptable, really, to Einstein, who thought in deterministic ways. He wanted a deterministic universe. And so Einstein was not happy about any universe that was traveling away. He had to recognize that things are moving away at there's a distance commensurate with the radiation that is measured. But he wanted, like many others, a steady state universe. Steady state universe and the Big Bang theory are the two main theories. After the Big Bang was produced, because there was a Georges Lemaitre, who was a Roman Catholic priest. And he had suggested and even calculated that maybe there was something like a cosmic egg, a primeval entity there, that exploded in a spectacular fireworks and created this expanding universe. And physics found plausible numbers for the cosmic abundance of different elements that would be created in that initial cosmic explosion. But when he went and presented his calculations to Einstein, Einstein said, "Your mathematics is impeccable, but your physics is appalling." And Einstein's reputed biggest mistake, according to him himself, was inserting what is called cosmological constant. That was a mathematical device that you put in that makes sure that the universe doesn't go anywhere. So there was in that era, 1940s, a Ukrainian-born American physicist called George Gamow, and he considered the early stage of this expanding universe. And he thought it must be a super hot stew of particles before, that is, having come from nowhere, all of a sudden it arrives. And George Lemaitre is very, very impressed, of course, with his thesis, because what he's doing is he's inferring that there is a creation event. Einstein and others and many scientists don't want a creation event. They want a steady state universe. And what is the difference? There are two problems that arise in any cosmology. One, where are things coming from? Let's call it the creation problem. And the other thing is an origin problem. For where is it coming? Now, the Big Bang doesn't solve the origin problem and does not solve the creation problem. But the steady state solves the origin problem, since we don't have to have one. There's a perpetual universe taking place. But it still has a creation problem. Where's the stuff coming from? And it's compared to some steam pudding with raisins in. You put it in the oven and it's going to expand. The heat makes it expand from cooking. And as it expands, of course, the raisins that you put in, they get lonelier and lonelier, so that when it's served at whatever time, let's say 6 o'clock in the evening, you have many, many raisins in your pudding. But as time goes on, the raisins become less and less. The steady state, however, says, no. There's a continuous creation of matter going on. It doesn't matter if you come at 6 o'clock or 8 o'clock, you will still have raisins on your spoon. But then the Big Bang people will say, my dear fellow, where did you get your raisins from? And the steady state people will say legitimately, where did you get yours from? So neither of them know where it comes from. That's the difficulty. Now, the Big Bang theory has become the mainstream theory to the extent that it has become touted in schools, universities, colleges as the very main legitimate, factual, cosmological model. And because of that, it's ignored many, many difficult problems. So let's go through some of these problems and see why maybe we should be a little skeptical. So let us look at the observations. First of all, we have an ideal potential situation by running the movie backwards, but we're stuck at the beginning. And so we have to say again that the redshift arose really from the Big Bang hypothesis. It was inferred by this Gamow and others that the redshift was simply what we call Doppler shift. But then we found out, no, it's a cosmological shift actually. And Doppler shift is, as I've described, something moving off into the distance and occasioned by the recession of those galaxies from us. So on the basis of this understanding, it was suggested that initially, some 15,000 million years ago, some 15 billion years ago, all the matter of the observable universe was collected in a very, very small space. And from that, this condition of compression, it somehow suddenly exploded outward, giving rise to the now observable recession. And it must have blown out greater than the escape velocity, greater than gravity can put it in. The only thing we know is that In the beginning, as it were, of all this development that we call universe, there's hydrogen, a little bit of helium and other things, but mainly hydrogen. And hydrogen doesn't naturally combine with anything, and it's all drawn in by this force of gravity. Gravity is pulling it in. Now, hydrogen is an electrical particle. It consists of electrical movement, positive and minus, as any atomic structure has. So that's all we know from observational evidence. We don't know anything else, except, of course, the theory that there may be this recession from this expansion. Or if we go back, now everything that we observe is in the past. So supposing we are able to trace how far light has traveled, we can read that. We can read that because we know its strength, and we can easily calculate how far, when it left, the time it left, the day it left, if you like. The problem with the Big Bang theory was that they discovered there were stars older than their projected date. Let's say 15 billion years ago. And the other difficulty was this. If you have a sudden explosion, then the particles are scattered everywhere, haphazardly. If a hand grenade goes off here, then fragments go everywhere unevenly. That's not what we observe in the universe. What we observe in the universe is something different. In the universe, we find that it is equal everywhere. It is equally homogeneous everywhere. Wherever we look, it is the same. We can go in every direction. So the person who invented this term Big Bang were these skeptics, these champions of the steady state. Fred Hoyle. Fred Hoyle, very well reputed astronomer and physicist, and his wife also, with an equal reputation probably. And they wanted to champion this steady state thing. They actually stated, says Hoyle, this Big Bang, it was a term of, a kind of derogatory term in a way, but has been identified as a legitimate term. He says it's an irrational process that cannot be described in scientific terms, nor challenged by an appeal to observation. There is really no observational evidence for it. So in these early models, they had to revise this whole thing of the Big Bang because from the very start, we have this problem. There are various problems called horizon problem, flatness problem. There are problems to do with what is called the helium abundance. There are many difficulties with this. And so what they did was to rescue it, was to put in, and a man called Guth and others were responsible for doing it, just an ad hoc theory called inflation. Because inflation smooths the universe out. Like a small bubble somewhere, and suddenly inflates. That sudden inflation, for no reason whatsoever, by the way, but we can theorize what has caused it. And so that solves the problems. And from then on, ad hoc solutions to problems have been given. That's the problem with the Big Bang, and it's a problem that remains, and it's a problem that has not been addressed. Gamow had inferred that this Doppler effect was there, but of course several problems have arisen, as I say, in connection with his interpretation. According to the current understanding, if all the matter of the universe has ever been confined in such a small space, its subsequent expansion would have been forbidden by its own gravitational encapsulation, what we can call a black hole, but the inflation solves it. And then we can say our second and third problems have got to do with the temperature of this fireball. At the required temperature, according to the current understanding, the fireball in its early stages must have been smooth, without any density fluctuations, and composed entirely of radiation coming from nowhere. And as the fireball then expanded and cooled, it suggested that the radiation itself gave rise to the electrical particles of the universe. So now we have a pre-hydrogen story. And then the universe is now seen to be composed of what is composed, but radiation cooling to electrical particles. That gives rise to equal numbers of particles and antiparticles, what we call matter and antimatter. But where's the antimatter? That's your second problem. There's no evidence for antimatter. You can create antimatter in a laboratory. The Large Hadron Collider that smashes particles into particles, hadrons, smasher, that comes up with antiparticles. But in the universe, we won't find it. If it was particles and antiparticles, matter and antimatter, then you and I would not be here to discuss it, because they would have neutralized and smashed into each other, and nothing, like reversing your car out of the garage and putting it back in, +1, -1, you're not going anywhere. So that is a bit of a problem. So how to solve this problem? And then the other thing is, if the universe expanded some, say, 15,000 million years, 15 billion years ago, from a fireball, then, as I say, this required smoothness would not be there. And so we'd be unable to fully account for the gravitational condensation of galaxies and stars within the still expanding gas. And so what to do? The rest is all ad hoc. Now, the ad hoc leaves us with another difficulty, and that is, from these models, the Big Bang inflationary model, there should be much more matter than what we find. It was fairly recently that it was discovered. In fact, it was discovered earlier, but really endorsed and absolutely proven beyond a shadow of a doubt, that when galaxies spin, when galaxies rotate, there should be a momentum differential between what is inside and what is outside. Newton's laws of dynamics will tell us that things will slow down so that by the time they come to a rotation around the edge and circumambulate in this way, they will be moving at a calculated velocity that is much less than the internal velocity. And when we look at it, we see it is not so. It is even throughout. Or initially there is a rise and then there's a plateau, but the plateau should not be there. The plateau should slow down. The curve should go down, and it doesn't. It remains. Another thing that is noticed is that when you study clusters of galaxies, there's a gravitational lensing effect. It is known from Einstein's general relativity that gravity has the effect of lensing, distorting the images. And this was also observed. And from this, the Big Bang people said, aha, we have found our missing matter. It is something that is around the galaxies. We don't know what it is. For this reason, we'll give it a placeholder term and call it dark matter. And then another discovery, some 5 billion years ago, the universe seemed to speed up by measuring candles, as we call them, or supernova. We were able to discover that actually this movement away from us started somehow to speed up. It's not consistent with the Big Bang theory. And so some other thing has to be invented. We don't know what it is, let us call it dark energy. dark energy and dark matter together comprise about 95, 96% of what we see, meaning that we don't know anything in the universe except 4% of it. And even the 4% is just calculated dust. So that leaves us with one of the greatest quandaries and difficulties and mysteries in the universe, and an attempt to find what is this dark matter. Since it doesn't radiate anything, it has to be dark. The only thing it knows is gravity. This also doesn't make any sense, because if the only thing it sees is gravity, it should be in the universe, in the galaxies, I should say, not outside. But these are forming hovering layers of dark matter. Now, there's no doubt that something is creating the slowing of the galaxies, and something, or sorry, the constant speed of the galaxies. Something is affecting it, and something is affecting gravitational lensing. So there are two solutions to this problem. One is called modified Newtonian dynamics. Modified Newtonian dynamics says the Newtonian laws that will predict the velocity of these galaxies may not work on those scales. Maybe if we modify it. This was originally proposed by a long time back. And when we make the calculations, we can make predictions. And the test of a good model in modern science will be if it makes predictions accurately. If all the data conforms to the predictions of a model, then it holds some credibility. The problem with the modified Newtonian dynamics model is it works in some cases, but not in others. But it makes some predictions. The dark matter model makes no predictions. And to be more accurate, it's the lambda cold dark matter model. And the candidates for that will be what are called WIMPs. These are weakly interacting massive particles. Because when you make all the computer models that you can, this conforms to what dark matter should be. It was originally thought that maybe these were neutrons, or I should say not neutrons, I should say neutrinos. But neutrinos, it was thought, should have no mass, and now we discover that they have some mass. So this has long been deleted as a possibility. Now, nobody has mentioned the formation of galaxies. In the formation of galaxies, there is a galactic wind that blows the debris out. Because when you begin with what is known and observed, that is hydrogen, helium, and a principle of falling that we call gravity, we found clouds of hydrogen that become so condensed that it creates a radiation. And the radiation creates irradiation. And that irradiation can be measured. And when we find the continuous irradiation of particles, we can measure it as a consistent 2.7 Kelvin, about 3 Kelvin. This was also work done by Hoyle. The initial prediction that there has to be some background radiation from the initial Big Bang came out initially as 15 Kelvin. Then it was revised to 5 Kelvin. Then it depended, because these calculations are making certain presumptions. But now you see in the 1960s, some significant thing happened. Two gentlemen called Wilson and Penzias, they were trying to find out by listening what the static was that they picked up, and accidentally they discovered what they declared to be cosmic microwave background radiation. And the Big Bang theorists declared this is the smoking gun we have been telling you all along, that there is now evidence, strong evidence for the Big Bang, and the echoes of it we can now measure. We can now see what they are. Now, the trouble with that, of course, is that the observational evidence was 2.7 Kelvin. And so now you have to go backward, and you have to now rearrange your calculations to force it into the 2.7 Kelvin. And that means you now push things back to allow time for this degradation to occur. And that then gives you a date for the universe, the origin of the universe, the time when this Big Bang occurred. Purely an ad hoc calculation. See, if our understanding of the rest mass of a proton is correct, that is, if it's really gravitational determined, then the greater rate of the expansion, then the smaller will be the rest mass of the protons. And it happens vice versa too. And since the expansion rate governs the size of the observable universe, therefore the number of protons for which each proton sees itself dispersed has to be calculated. And curiously enough, this actually gives us a governing mechanism on the expansion rate. The larger the expansion rate, the smaller the observable universe. And that is the figure that determines the rest mass of the particles. And the lower the rest masses, the slower their rate of gravitational collapse. And therefore the radiation rate, which drives the expansion, has to conform to that. The smaller the expansion rate, the larger would be the observable universe. And that determines, of course, the rest mass of the particles. And the greater their rest masses, the faster their rate of gravitational collapse, and the greater is their radiation rate that drives the expansion. So it's a light in the light of those kinds of considerations that we can suggest the smallness of the proton is exactly the same thing as the largeness of the universe. And changing one changes the other. So it's the ratio of the smallness of the proton to the largeness of the observable universe that determines the rest mass of protons. And that means that the boundary imposed at the moment by the observable universe, by this expansion, a borderline created by the redshift, is of the nature of an event horizon. So an observer can see anything cannot see anything disappear beyond it. We don't know what is there, because it's something that is seen to approach the border or the boundary, if you like. And that's the speed of the ascension that approaches the speed of light. If that's the case, then the radiation will be seen to be redshifted toward zero energy. And that is its clocks, or its internal motion, if you want to put it that way, will be seen to be redshifted toward a stop. And its progress toward the boundary. If you ask, is the universe finite or infinite? Well, from our observational point of view, the border makes it finite. So that will stop along with the motion of all clocks. And it will be seen to be redshifted toward a stop. Now, as seen by us, the energy of the radiation from distant particles appears to be redshifted. Then, as seen by us, and we have to always say as seen by us, the energy of those particles themselves, and that means their rest masses, must also appear redshifted away. So this apparent loss of rest mass of particles near the boundary can clear up the understanding of the boundary in two significant ways. First, the radiation reaching us from the region of low rest mass must come thermalized in black body radiation at a very low temperature. That's what we find, 2.7 degrees Kelvin. That's what we measure. And secondly, the particles themselves may be recycled back into the observable universe through the uncertainty principle that I mentioned. Heisenberg's uncertainty principle relates the observer to the observed through a necessary uncertainty. And so the momentum of the observed particle is put in such a way that if the uncertainty of the momentum of the particle approaches zero, the uncertainty of its position must approach infinity. We don't know where it is. And as the mass of the particle approaches zero, our uncertainty as to its momentum must also approach zero, because that momentum itself approaches zero. But if the uncertainty of the momentum approaches zero, then as the particle nears this boundary, then the uncertainty in its position must approach infinity. And that means we can no longer say that it is near the boundary, we can no longer determine by any measurement that it is there. And so, just as black holes leak, this boundary must also leak. Now we can understand where your steady state raisins come from. So that is a theory that is worth understanding. It is a kind of recycling theory. And so from this standpoint, we can understand that there's not just one creation, but a continuous creation required. Now, in the Hindu way of thinking, this recycling universe is a given. But there are two understandings of it. Either there is an origin, that is, there is a potency called Prakriti that emerges, as it were, in a moment and evolves for eons of time, some trillions of years of time in our calculation, and then goes back equally, back to its position of potentiality. And so it goes on, a recycling that goes breathing in, breathing out, something like that, a breath in, a breath out, a cosmic breath out and a cosmic breath in over eons of time. That idea is there, but because we can accept, according to the various Vedic models, parallel universes running in concordance with each other, then this could also be localized. And Swami Vivekananda would have considered these two options. And he would have said, more than likely, it is a localized inhaling and exhaling. It is a continuous creation and dissolution occurring all the time. And so this continuous creation is required by any steady state model. And it provides us with, where did the steady state people get their raisins from? It's continuously being created. And if we postulate this, then we have to ask, is there any evidence for it? Now, I think we do find evidence for it, because we can find in the various quasars new pockets of hydrogen being created in the universe. Don't forget, the Big Bang wants everything to create everything in one go. No new creation of hydrogen should be there. And yet what we observe is new pockets of hydrogen coming. And that means it's recycled from the border. Just as black holes will leak, so also this can come back into the universe. And so the universe now becomes a continuous thing. But where do we get this expansion drive from? Where do we get this dark energy from? Well, energy cannot go nowhere. If energy is expended in the radiation, it must come back to drive it. And so it's no mystery according to this way of thinking. Now, this is a much more feasible way of looking at things, I suppose, than inserting ad hoc events and solutions in order to try to neutralize the various difficulties and flaws. And I would then say that this Big Bang theory is full of rags and patches. Just to give you some examples of these rags and patches, I can tell you systematically. Of course, we've come across one of them, two of them already, probably more. First one, don't forget, is where is this coming from? The first objection, the first problem is you cannot get something from nothing. What was the something that was there? So let us see some of these problems systematically. I'm referring to an article on it here, so bear with me as I do this. And it will tell us in a simple way. So I'm reading directly from this article. If the explosion had gone off at a greater than the escape velocity, so that gravity could never have halted the expansion, then nothing in the universe could ever have run into anything else in the universe ever again. So we could never have gotten galaxies and stars out of it. And he gives the example that I gave, that is commonly the example given for the death originally of the Big Bang without any modifications. If a hand grenade explodes in midair, the pieces of the hand grenade do not run into each other. But cosmological models which do not allow for galaxies and stars are considered to be flawed, says this author. So those old models have been laid to rest with headstones in the graveyard. But even if the explosion had gone off at less than the escape velocity, that is the collapse, as soon as the collapse of it, it would still have been no better, because then the universe would long since have collapsed to what is known in the trade as the Big Crunch. So those models too have been laid to rest, and this has left us with this problem. Why should this accidental approach or this accidental explosion have gone off at just the escape velocity with such very tight constraints? And this problem we patched with the anthropic principle, which says that there are over 20 constants which are exactly correct and exactly right. So since we know from quantum mechanics that there is no longer any talk of a universe without an observer, now I have to clear that up a little bit. The greatest mystery in the quantum physics, regardless of what avenue you take, would be what is called Young's double slit experiment. It's an experiment that tries to determine exactly where a particle is and its momentum simultaneously, and Heisenberg's principle says you cannot do it. It's derived exactly from this experiment, that when you put any subatomic particle through a slit, it will arrive as scheduled on a scintillating screen at the end of it. But when you open two slits, then it behaves like a wave, it interferes with itself, and then converts itself in a wave pattern as particles on the scintillating screen. And what is the key? The key is observation, be it through the eyes or some interfering mechanism that disturbs the coherence of the waves. And this point of disturbance of the coherence is called decoherence. And the decoherence point, we know more precisely, it's actually at the upper limit is at the molecular level, creates the world that we have. That is, the world in what philosophy we call the waking world of chairs and tables and this and that, is actually an untypical example of nature, so that a great physicist called Leonard Susskind says, what we see in our familiar world, this deterministic world, is just an approximation of what is. Now, as I'm speaking, you will surely come to some conclusion that the ancient philosophers came to, that this world that we observe, this universe, this whole cosmos, is mithya. That means apparitional. That means it has an apparitional cause to it. And technically, this apparitional cause is called vivarta. It is a mistake. And we have in our philosophy a number of examples for it. The most famous example is in the twilight of the day, when things are not quite clear, you see something coiled up and project onto it the concept of a snake, something that is dangerous. But in the light of knowledge, it becomes revealed. And these components being there, its reality being hidden, its concept being projected, and the capacity to reveal it as it is. But the clue to the apparition lies in what is revealed. What is revealed is a coiled rope, not a snake. And that means that when we mistook it, it has all the signatures of the rope. It has length, it has breadth, it has coiled up appearance. And so this universe, as we see it now, must have the clues contained within it. So we'll come back to that because this is useful in understanding of this cosmology. Now, on quite independent considerations, the early Big Bang models had another problem. Why is the universe made of matter rather than half matter, half antimatter, which would have just eliminated it completely? And so it had long been known that radiation cooling off to material particle cools off to 50% of one and 50% of the other, and that will all just disintegrate. Then the problem was patched. What was the patch that was made to solve the antimatter problem? A particle was invented. It was called an X particle. And the purpose and role of the X particle was to manufacture matter into antimatter, and the anti-X particles have to be invented, which make antimatter into matter. And then since the X particle, which is a proton, decays more rapidly than the anti-X particle, you just make it like that. You have to push it in. Then we're left then with a preponderance of matter of antimatter. In fact, what we are now, therefore, is just the residue. Then, since this X particles decay more rapidly, we are left with this, and that seems a splendid solution. But the anti-X particles, which decay more slowly, they decay to what is called magnetic monopoles. If you take a bar magnet, two poles are there. A plus and minus monopole, plus and minus are there. But if you eliminate the one, then you only have one pole. And these are called magnetic monopoles. The problem with this is we've never found any. There's no evidence of them. So that's another problem, the problem of the magnetic monopoles. So this monopole problem is there, and how do we get rid then of this problem? Well, you can automatically yield a universe that expands beyond the escape velocity so that we don't need the anthropic principle. And that seems good, but that gives us another difficulty, and that is the dark matter problem. Most of the matter in the observable universe would have to be something which we have never yet discovered, something invisible which responds only to gravity. Otherwise, the predicted helium abundance in the model would be wrong. Now let's go back to this formation of galaxies. When stars and galaxies form, a blast is made by the solar winds or galactic winds. They don't go very far. These are minute particles of dust, gases and dust, actually, which eventually cool and condense and form what we might call a hovering layer around the galaxies. And when you ask physicists who know anything about this, they can give only approximation that ranges from 90% of the matter formed to 95%. But none of this is mentioned because we have to have an exotic material called dark matter in order to support this cosmological model. So we have many myths from this past which are to do with cosmological models. For example, there's Babylonian Cosmology, which says around about 3000 BC, which tells us of a flat earth floating on infinite waters of chaos. We have mythologies of turtles. Everything is on the back of a turtle. And then, of course, the famous question answer session. Well, then who made that turtle? Oh, that's sitting on the back of another turtle, and so it goes on. And sometimes that's expanded into, oh, it's on the back of an elephant. And where the elephant come from, you have another infinite regression of elephants going on. So the myth that we have today really is the Big Bang, with many ad hoc solutions invented to try to support what is really a creaking model. And I suppose what I'm saying is, we would be happy to accept and endorse any model if the observational evidence was there for it. But what is observed is made into observational evidence for a hypothesis, which has really not been endorsed. And so many people have a problem with this model. One of the great originators of the inflationary addition to the Big Bang model that smooths the universe out and solves many of the problems, such as flatness problem, horizon problem, and so on. Paul Steinhardt is his name. He has now created some version of the cyclical model, which is just as detractors will call this Big Bang model Big Bang. Now they're calling this kind of model a Big Bounce. But it still requires dark matter and exotic matter. And the idea is that we don't have a singularity that does away with that problem. We have a series of universes that are connected with membranes. And because gravity is the weakest of all the forces that we have, perhaps it's because the energy from gravitation that we find here is dissipated in another universe. And this comes as a membrane that collides from time to time and creates a bounce. And this is called the Big Bounce. And there are other versions of cyclical models. Now, the problem with cyclical models is this, that if you come to the end of your universe, all the energy has to be gathered to make another universe, and that creates a continuing addition and summation of energies going forward. And so you now have to disband this holy principle, which is the conservation of energy and matter. You're now adding to matter. That's the difficulty with it. But the Vedic models are cyclic models, and they don't have this problem because at the end of the cycle, everything goes to zero. Nothing is carried forward. So there's no big bounce involved in it. There's simply a complete annihilation of everything. So this predictions, of course, some of the early predictions of the Big Bang model was the cosmic abundance radiation of hydrogen, which I've mentioned, and the two isotopes of helium, deuterium, and lithium. This was long ago confirmed observationally, of course, and was one of the very strong arguments for the Big Bang. and against the steady state. But the early prediction would hold true only if not more than 10% of the matter in the observable universe predicted by the inflationary models is ordinary matter, out of which those substances could be made. And so consequently, the inflationary models predict that some 90% of the matter in the observable universe must respond only to gravity and not to nuclear forces or to any other forces such as electricity, magnetism, which might allow us to detect it. So immediately, this idea that there is some gravitational force that seems to be affecting the rotational velocity of galaxies, and that there is gravitational lensing, immediately the Big Bang theorists say, there is the solution to our problem. Now, just because the Big Bang still has problems doesn't mean that the steady state, the alternative model, is right. And just because the steady state had problems, it also doesn't mean that the Big Bang is right. These are the two key postulated hypotheses of the 1960s. The fact that we can think of only two models doesn't prove that one of them is right, and maybe you have to go for another one. So I've mentioned a number of these difficulties, and I've mentioned some solution. And so we could look at the border of the redshift for our solution, and that's exactly what we have done. That the particles simply tunnel in from the border is certainly a feasible alternative that matches with observational evidence of new pockets of hydrogen that we can observe. So let's just see how the time is going on this. Oh, we've long gone over our time on this, not even allowing for questions. I just want to see how things look from the Vedic point of view. There's a cosmological model there. We can say there are two cosmological models. Now, we've mentioned the apparitional model. But Vedic cosmology really is encapsulated in this Nasadya Suktam. I made reference to this in a thought that I put out the other day. So that goes like this: Nasadasin no sit taranim. Then even, that is, at the point of where we're speculating there may be an origin, non-existence was not there, nor existence. It's a wonderful thing. There was no air then, that is, there was no potential energy then, or kinetic energy then. There was no space beyond it. And what covered it? Where was it? And in whose keeping? Was there then cosmic fluid, what we call plasma in modern physics terminology, in the depths unfathomed? Then there was neither death nor immortality, nor was there then the torch of night and day. That one breathed windlessly, that is, without energy. And self-sustaining, it wasn't caused by another. There was that one then, and there was no other. Now, if we have a universe, there still has to be no other. At first, there was only darkness wrapped in darkness, such a beautiful poetic term. Can you imagine? Darkness covered by darkness. All this was only unillumined cosmic water, that one which came to be, enclosed in nothing. Water, because water is the potentiality for formation. Water can form itself into any form, any mold you put it into. And it arose at last, born of the power of knowledge. That is a knowing conscious entity. In the beginning, desire descended on it. That was the primal seed, born of the mind. And the sages, that is, those with great insight into the subject, who have searched their hearts with wisdom, know that which is kin to that which is not. And they have stretched their cord across the void and know what was above and what below. Seminal powers made fertility mighty forces. Below was strength and over it was impulse. But after all, and here's a beautiful statement of agnosticism, who knows and who can say whence it all came and how creation happened? Because you and I weren't there. The gods themselves are later than creation. So who knows truly whence it has arisen, whence all creation had its origin? The Creator, whether he fashioned it or whether not. He may know, or maybe he knows not. All of this kind of understanding was there in this. So now, I can't leave you there, unfortunately, even though time is moved away from us a little bit. The Vedic concept was like this. The law of nature is constant everywhere. When we, through our observational evidence, see everything rotating, that is, when we see this concentric acceleration that is going on, then we might infer that the whole universe is also rotating. And so it postulates that things began with an initial spurt, initial start to rotate, and then a failure, and a start to rotate that eliminated the antimatter, and starts a rotation. The problem with the rotation model is, and it has been entertained by a number of cosmologists, is it requires an axis. And when an axis is there, it means that there has to be parity, or that has to be, I should say, a disruption, a violation of parity. Parity means things are equal on both sides. But when something rotates, then there's an emphasis, there's a concentric emphasis on one side. And we would find evidence, if we found evidence of a violation of this law of parity, but we do find it. We find it when we examine the weak forces in physics. And this really became a revelation. Some people saying, we can't believe that God was a weak left-hander. So there was, but this has actually been absolutely proven to be true. Again, if we take the laws to be constant everywhere, then we would also find it in the universe. And there seems to be some evidence for it, which is much, much disputed. So there were two independent scientific teams, one in China, that managed to find this violation of this parity. And I will tell you their names. I'm just looking for their names now. These horizon problems are there and so on and so forth. If you want more information about this, I can tell you. Entropy problem was another one. Okay, so we have seen that modern scientists consider the universe resembling the surface of a sphere. This is the way that the ancient Vedic cosmologists would have thought of things. And therefore they call this something like a cosmic egg that divides into two halves. So because they have reasons to believe that the universe is isotropic, closed and curved. So what considerations have led these sages to this representation of the universe as an egg? Then the answer comes in rotation. I'll give you a simple example. If you take a small drop of water and you start rotating it, it flattens out into a sphere and has a surface of a sphere. And that means that it has certain characteristics. So they see the universe as rotating something like a wheel. Don't forget, that's not the origin of it. The origin of it, according to the Vedas, would be vivarta. It's apparitional. It looks something like it is because its evidence is there. I'll just go back on that a little bit and say, what are the evidence? Gravity is seen to be the evidence. Supposing you have annihilated the whole universe through certain forces, space and time has been eliminated. Special relativity can do it for us. I can go into that more if you want. Supposing energy and matter has been eliminated, supposing it's all energy. Supposing that kind of energy is gravitational energy and electrical energy, we find that they operate in and out at the same forces and eliminate each other. You don't have a nothing. You still have a something. What is that something? Gravity is there because it wants everything to fall into a oneness. It doesn't want everything to divide. Electrical energy wants the division. It wants things to fly off to infinity. And so could it be then that gravitational energy is evidence of something that is undivided? That time and space makes an appearance of a will to undividedness. And supposing you have this electrical energy that makes things fly off, is this evidence then of an infinite? And if you have inertia, when things move, they don't want to stop, is this evidence of an unchanging? And so we cannot say with physicalists, if you make all this elimination, we can get a universe from nothing. No, this is a far away from nothing. That which is undivided, that which is infinite, and that which is unchanging, that is far from nothing. In fact, it is everything. And when you impose this apparitional, just as this snake is superimposed on a rope, then you have this evidence of the rope in this unchanging, this undivided, this infinite, as gravity or gravitational energy, electrical energy, and inertia. This symmetry will be there in the axis of rotation, and that is why the symbol of the universe would be a chakra, a wheel. And when they discovered this violation of this symmetry, the famous physicist Wolfgang Pauli, who is a Nobel laureate and has the Pauli exclusion principle relating to electrons, he wrote a letter saying that he did not believe that the Lord is a weak left-hander. Now, there was an experiment conducted by the female physicist called Chien-Shiung Wu, which was some time back. And a few months later, it was confirmed by two physicists, Li and Yang. And Li and Yang, of course, were in the 1950s, late 1950s, early 1960s, awarded the Nobel Prize in Physics for their discovery. Wu received the Wolf Prize in Physics in 1978. This is for this, in weak nuclear forces, this violation of parity. So this parity violation, of course, means that nature distinguishes between left and right. And then the question would arise, how does it arise in an isotropic universe? Now, the range of electromagnetic and gravitational interaction is almost infinite. The range of strong interaction is 10 to the minus 15 meters, and that of weak interaction, 10 to the minus 17 meters. So weak interaction has the lowest range of all the interactions. So it is very, very difficult to prove on a cosmological scale how this would work. With such a level where the rotation of the universe affects the conservation laws. And of course, it has been a while since this original violation of disparity was there, but the University of Rochester had somebody called Borg Nordland, and another one, John P. Ralston, of the University of Kansas. And they both found evidence of a preferred direction in the universe. And they published their results in a Physical Review Letters, the Scientific American, in July 1997. They published a one-page report on their findings, and they called it Science and the Citizen. And after 3 years of painstaking research, both of these, both Nordland and Ralston, have found that polarized light from galaxies shows evidence of rotation. I'm reading from the article here. The twisting of polarized light is a well-known fact or a well-known phenomenon called Faraday effect. However, this rotational effect is on top of the Faraday effect. In other words, that's taken into consideration and depends not only on the distance of the galaxy from us, but it depends upon the direction of the galaxy as well. The rotational effect is strongest in the direction of the Earth's sextant's axis and is weakest in the direction of perpendicular to it. And Nordland, I should say, and Ralston have ruled out the possibility that the effect is local. The effect is at a cosmological level, as it depends upon the distance of the galaxy. Now, the work of these two was greeted with some great deal of skepticism. It was challenged by scientists. And when you challenge it, you all have to say, maybe the analysis is wrong. So that's only to be expected. Physicists are not going to abandon one of the most cherished beliefs about the Big Bang so easily. So it has to be backed by further evidence. But both of these two independently, Nordland and Ralston, have maintained their position that their analysis is correct, and they have produced data to endorse that. They've stated that their result cannot be explained by conventional physics, and the effect may be due to an unknown force of field or property of space, namely the rotational, I'm adding to this, namely the rotational hypothesis. But of course, to those who feel that the ancient sages must have been correct, they might be saying that the result explains actually by conventional physics, and the effect may be due to an unknown force. No, that is actually due to the rotation of the universe. Evidence for this. That is what they come to a conclusion on. And so this could be an endorsement of Vedic cosmology. And it solves many problems. First of all, singularity problem goes away. Secondly, all the other conservation of space and matter and energy is kept in preserved. I have to explain that. The singularity required for the Big Bang flouts the conservation of space, matter, and energy, because you don't start with it, you start with a nothing. Nothing is preserved. Another aspect of this is that gamma ray bursts may well be an explanation also of that binary neutron stars are collapsing, and there are problems with that explanation. But the gamma ray bursts maybe are intense bulk of their radiation. Their range is in the range of 100,000 to 1 million electron volts, and they imply a very hot source. And its sources release more energy within minutes than the sun will release in its entire lifetime. Now, astronomers, of course, believe that these bursts are coming from cosmological distances, probably 3 to 10 billion light years away. And the source of these bursts are distributed isotropically. That is, of course, isotropically means it's the same in every direction. But the question, of course, is why? So are we, just as I thought, in the center of a large spherical shell over which the source of these bursts are uniformly distributed? And the idea of us being in the center of this shell is, of course, unnerving to most scientists, because the center is a position that science does not want to be. It goes back to pre-Copernicus era. But we have seen, of course, we see when we study the Vedic scientists contained in the Vedas, that the creation of mass and energy is taking place continuously at the surface of the universe, that is the surface of the spheroid. And we've also seen that the creation of the mass and energy is related to the expansion of space. So as the universe is huge, now at this point, its expansion will create immense radiation. This then gives us an explanation for the whole evolution of the universe. Possibly even what we are seeing as an expanding universe is just that eccentric position in the rotation of the entire universe. These are ideas and possibilities, but certainly the current cosmological model has many, many question marks over it and many ad hoc inserted solutions to solve these problems. I could go on, of course, forever, and I won't. So if you're already asleep, don't worry about it. I understand the subject matter is of that nature. Where does that leave us in terms of the Vedanta? It gives us a very, very concrete idea of that which is not concrete. That is the transience of the whole universe as such. It gives us an idea that if these alternative models are correct, then the laws of nature are constant. And by studying one small aspect of it, we can get to grips with the entire universe. It gives us a different perspective on the materiality of what we endorse to be real. It gives us a concept of the immensity and the infinitude of things. It gives us a sense of wonder, a sense of adoration and thankfulness also that goes with it. It gives us a curious mind that we should not really accept everything ad hoc, that we should learn to question it, that we should not go along with dogma and doctrine, be it of the religious kind or the scientific kind. So these are some ideas arising from this talk. Bearing in mind the lateness of the hour, I can open for a few basic questions, but then if not, we'll leave it. Nothing? My personal belief, therefore, is Big Bang. It does not hold any water. It's a theory that is full of rags and patches. It is the only theory that we have sustained for so long, since the 1960s, that if it were any other theory, we would have abandoned long ago. But the whole research at in the Large Hadron Collider there in Switzerland depends on this idea that there was a Big Bang. The whole of our research into dark matter, dark energy, is reliant on this idea that there was a Big Bang. The whole scientific perspective that we only understand 4% of what is entirely reliant on this theory of the Big Bang, with no explanation about how it came to be, where it came from, how it arose, how we've survived with ad hoc particles being inserted to solve the antimatter problem, that how we had to invent inflation, an inflation model, and how we've written it into the dogma without any shred of evidence for it. And so if there's anything, it is that we should, you may not agree with me, but at least, and as I say with all the things I present, I'm not looking for agreement. I'm looking for you to think differently, to shake your thoughts up and have an inquiring, creative mind. All right, good. If there are no comments, if I've left you completely numb now, then we'll leave it at there. Yes, oh, somebody has a question. Good.
See the split theory. You spoke about that before, and I'd watched some of it on YouTube. Is that sort of giving us the lesson that you get what you focus on. You know, where they focused on the photons, if they expected them to go through one slit, they would go through, and if others observed them and expected them to go through another. So is that the way we should be thinking of our own life and our future? Is that the lesson we should be getting from the split theory? That nothing is the reality until you sort of observe it as such?
Well, there is one school of thought that says that the observations in the double slit experiment lead us to a conclusion that everything is consciousness, and that would explain everything. And people like John Wheeler and others would have gone along with that idea, and that means then that things only exist when we observe them. That would be the idea of it. It is one explanation, it is one approach, what we might call an interpretation of the phenomena we find centered around the double slit experiment. I don't think it's the only explanation, though. But there's no doubt that what we expect arises as a thought, and provided the expectation is not so much an expectation, but an intention that is sustained, we surely know that it will condense in the universe either now or in time to come. There's no doubt about that. But you see this idea, this wave-particle duality problem, as it's called, in the double slit experiment, has a number of interpretations. There are three popular interpretations. The one is the conventional orthodox interpretation called the Copenhagen Interpretation. Not so much an interpretation as a statement of facts, but it requires us to hold things in an indeterministic state called superposition, so that things are not actually there until we look at them, and then that collapses the wave. This can be done either as literal observation or as interference with something that also has to interfere at the quantum level. And when we then bring it up to the decoherent level, it comes out of focus, as it were. So this is one variations. A variation of that Copenhagen interpretation would be the observer has to be a conscious observer, even when it's done remotely. And then, of course, John Wheeler was very keen to extend this experiment. And so he made a number of experiments which came after the slit to show that actually whichever way you play it, whether it is before the slit, actually at the slip, at entering that, or afterwards, once it's gone through, this is called the delayed eraser experiment. That whichever way you look at it, when you observe it, it changes its behavior, so to speak, as if it were a conscious particle. Then the question arises, but the universe itself, how does it arise? Since we observe it, and we weren't there at the beginning, let's assume a Big Bang, then how did it arise? There must be an observer. What was that observer? Now you come to cosmic mind. Cosmic mind was the observer, where is the conclusion that it comes to. So that's another take on it, as it were. So these are various interpretations, because it's the one area of physics that we have no explanation for. We don't know why it happens, and we don't know how it happens either. Now there's one other explanation for it, which is called many worlds interpretation. Many worlds interpretation says, before this happens, before it enters into the double split, it splits off into infinite worlds. This is called the Everett interpretation also, and it has been adopted quite popularly but yet not popular enough to be adopted as a conventional interpretation. But it just is, again, an ad hoc interpretation that does away with all the difficulties and obstacles because you don't require superposition. Not quite. It means that you have infinite superpositions. So it doesn't really solve the problem. And the problem was highlighted by Schrödinger, because Erwin Schrödinger, he put this out as what's famous called Schrödinger's cat. You put a cat into a box and you close the door and you arrange things in such a way that there's a cyanide drops on a decaying radiation, and then the cat dies. But does it die? Since that is a possibility that is not determined yet, it is literally half dead and half alive, and we only find it out when we look at it. But of course, that presents its own problems. But he was highlighting the absurdity of such a position. He has a conventional position. I think more absurd would be the many worlds interpretation that says that there is a duplicate of ours infinitely in every universe. While I'm sitting here, I'm also cooking food in another universe. And even in one of those universes, you'll find Harry Potter will be there. So this seems very way out, much more way out than saying, as maybe some theists will do simplistically, God did it. That seems to be the Occam's razor position, which is much more feasible. And so that has its problems too. And then there's another two, really, which one will say that we are only observing the peaks, that things come in peaks, and those peaks are summation of those peaks is what we're measuring. And another interpretation is called the Bohmian interpretation, which says actually the wave was already there. And David Bohm gave it more a holistic understanding to say this whole world is a wave system and particles are actually really there, but they're at the peak of a wave. And so when they go through, the double slit, they go through as a wave, they get carried as a wave, they interfere as a wave, and they arrive on the scintillating screen with a wave pattern, and the particles are clearly defined. Now, the problem with that is it requires an unknown additional force called a wave force. So the wave aspect which is really a mathematical construct, is seen as an actual thing, an actual force. So these are the various difficulties and problems with it. All right, we'll leave it at that.
Thank you.
Thank you, Swami.
Okay. You all understood everything perfectly?
Oh, absolutely.
The thing is, it's not important. What's important is to rake up the mind a little bit and think a bit, see? And if you get 1% of what we said today, that's good.
Yeah.
Think differently, change your way of thinking. Don't accept everything gratis. Make a challenge to it and make your own discovery and research and find out what is feasible. It's my prediction that because the Big Bang, supporting the Big Bang theory has cost billions and billions of euros and dollars and so on.
Yeah.
So to abandon it is an expensive thing to do. And nobody likes to abandon their most cherished views, not understanding that a mere hypothesis has been given the status of a theory, which in turn is really put into all the literature as a fact. So you'll find in all scientific literature at the time of the Big Bang, when the Big Bang happened. And I think we will awaken to it. And probably in the next 20 years, I would think we will abandon this whole theory of the Big Bang. It just it won't hold up. It will limp along. And already there are dissenters from it, trying to find some alternatives. I think the alternatives will be in cyclical models. And these cyclical models are completely found in the Vedas. These are Vedic models. And don't forget these early pioneer scientists, Heisenberg, Schrödinger, and others, relied on the Vedic way of thinking for their scientific solutions. Heisenberg went and saw Tagore, I think it was, and asked him, look, you know, I know that in your Vedanta philosophy, you have weird and wonderful concepts. I have one. I just want to check with you whether this could be feasible. And so he was adopting these ideas, you know. Einstein adopted them also because he was a fan of Spinoza, and Spinoza was a panentheist. Panentheism we find in Vishishta Dvaita philosophy in the Vedanta. So in order to understand modern physics, we really have to go to the Vedas, is a bottom line on it. Not even accepting them, but testing them out. And one test would be if we find this violation of parity, then we know we actually have a rotating universe, which finds a border. And at that border, we find Heisenberg's uncertainty principle kicks in. And we have a recycling model where at the border, these subtle electrons tunnel back in. These particles of hydrogen tunnel back in. They cluster, they form new clouds of hydrogen. And then we have this renewable universe continuously, which means that the expansion is a temporary one, and the universe, as predicted, doesn't end in a cold, dark death, nor does it end in a big crunch. It just perpetually goes on forever, ad infinitum. All right, we leave it at there. Om Shanti, Shanti, Shanti. Peace, peace, peace be unto all.